Oh, so you're defining the F event.
delta P
Yeah.
as the thickness of our sphere in momentum space.
Yeah.
And then I just said Gamma, this is the Gamma function.
I didn't say
Just because it's one of the things that wasn't.
Well, that all sounds familiar, the thickness of the sphere in momentum space.
Hey, yeah.
Right, crystalline structure, instinct.
Periodic or not for that
First
conditions?
We didn't do
I don't think it's the same exact thing. Okay.
Yeah.
You're surely eventually gonna do
Yeah.
that. You just have to. I don't think
Yeah,
you can stack neck without that.
This is what I meant.
Dr. Harmon.
It's the Einstein model section.
Okay, yes.
First thing is
So
crystalline
I
structure.
applied to
And that's what that question
go
was.
to the SPS on their congressional visit
That's why I did.
in March, and I got accepted.
Nice.
So I'll be gone for like a week, and then like right after spring break.
Oh, really?
Okay.
I'm gonna be gone from March 19th to March
Somebody will watch
22nd.
my videos!
Yeah, someone will watch
Alright.
the video.
All right, awesome.
Yeah, but I'm just excited. I
Yeah,
learned
that's
today.
cool, excellent, congratulations.
Thank you.
Yes, indeed.
It's been a good week. Been nominated for the Meet Leadership
Silence
Award.
of all
Yeah, got the visit day thing. I think my internship with Dr. Mack is finally being confirmed.
Yeah, cool.
Nice. Everything's kind of like converging. It's like,
All right, good.
let me have a future.
Yes, I'm all for that. I want you to have
What is a future? What is
What
this
is,
abstract?
what is time?
Yes.
And why does it seem to have an arrow? And now we're getting really deep. No, let's just do degeneracy pressure. That's much easier. Let's do the Chandrasekhar limit. So last time we discovered that if you find the classical speed of electrons in series B, it's faster than the speed of light, which means we don't believe it. So, let's consider the extreme relativistic case, where basically all of the electrons are relativistic. Assume that it's such that essentially for the entire Fermi sphere, all the electrons are moving at near the speed of light. So we can use the relativistic, you can always use the relativistic expression for the kinetic energy, but in other words, the extreme relativistic limit where the energy is just the momentum times c. So in other words, remember that in general, E squared, if we go ahead and use unnatural units, is mc squared squared plus pc squared. That's the general relation.
Did you forget to add the extra square?
I sure did, thank you. Yes, I sure did, yeah. Uh-huh. Well, that first term there, mc squared, is fixed, right, for a given type of particle. So the more momentum the particles have, the bigger the second term becomes compared to the first term. So we're interested in the case where that second piece is much bigger than the rest energy. And that says that, to a good approximation, E is just PC in that limit. And if we put in the quantum mechanics, that would be h bar k times c, since p is h bar k, where k is the wave number. So we're going to consider the extreme relativistic limit here because that's easier than having to add in the mc squared squared term. So let's consider the extreme relativistic limit. All the electrons are relativistic inside our white dwarf instead of just the most energetic ones, with E equals PC. We'll just set the energy equal to PC here. Equals h bar k c here. H bar k c. energy of the electrons is then, we're going to do that same integral we did before to find the total energy and then take its derivative with respect to volume to find the pressure. But instead of using the classical p squared over 2m, h bar squared k squared over 2m for their kinetic energies, we're going to put in h bar kc instead for their kinetic energies. So our expression for the energy becomes the integral from 0 out to k Fermi, h bar kc, so that's the energy, right? That's the energy of an electron. With a given value of K. And then I'm going to start putting in the other terms, and you're going to tell me what each one means. Or at least in my dream scenario, you're going to tell me what each one means.
We shall find out.
We'll find out, right? Or it'll be, I'm just going to go back to chapter 1 and try to figure out where we, so V over pi cubed. Remember, what was that? Volume of the container over pi cubed, that was the, yep, go ahead. It's the number of states per unit volume, the density of states, as we call it in K space. So that's what that's usually called, so I'll just call it that. The density of states, the number of states per unit volume of K space, density of states. Times 2. 2 is spin, yep. That's the spin degeneracy. Each state gets 2 electrons. Yeah, you got it. It's like you're reading my mind, times 1/8, because we only want the positive octave. Times, now we need the volume of our shell in K space, which is?
4 pi p delta p.
We're doing it in K space. 4 pi, not K.
K Fermi.
No? The thickness of the shell times its area.
K squared.
K squared, I actually need area. So 4 pi k squared dk. So that's our expression for the energy now. The only difference from what we did before is before we had h bar k squared over 2m here. We had the classical kinetic energy here. Now we're putting in the relativistic energy, h bar kc. So notice then that what's going to lead to the difference is before this was k squared, now it's only k. And so that means that the energy's dependence on k Fermi is going to look different now because of the fact that there's only one power of k in that term. So this is h bar c, volume to which they are confined, pi squared, integral from 0 to k Fermi of, now it's k cubed dk, instead of k to the 4th power dk.
Isn't it pi cubed on that side?
Let's see. No, because there's a pi in the 4 pi k squared dk. Yeah.
In the back of the 4 squared.
So of course now we ask Mathematica to do the integral for us. And yes. And then I stomp on your laptop because I'm so in the wait with you for doing that.
Mathematica's working, man.
But it's still running it. Takes a lot of calculation.
I downloaded it and it just asked me for a new activation key and like you're able to snap it. It's all good. Just like delete some packages and then it'll reload everything. I'll try deleting that. There's only certain things that you need to delete.
So h bar c volume over pi squared, 1/4 of k Fermi to the 4th power.
HYCB.
Yeah, and now we put in what k Fermi is again, in terms of the number density that we got before. So h pi cv over pi squared, 1/4 of the Fermi wave number is 3 pi squared times little n number density. So we, to the 1/3 power, so we put that in and we raise it to the 4th power, so the exponent becomes 4/3. I'm sorry, am I boring?
It's 2 o'clock now.
Yeah, that's it, yeah, the afternoon, time for a siesta.
Yeah.
Yes. Those are actually, those are such a good idea. I mean, your productivity goes way up after a little nap. You know, that's great. Is that Spanish or did that start in Spain
I
or?
believe so.
Yeah.
I mean,
Because I think of it as Mexican, but.
it's inherent in, I think all Latin cultures.
Yeah,
So,
yeah, they're smarter, okay.
well, you better take that.
I still remember watching a news broadcast once where they're talking about like pilots taking a nap in order to be better ready to fly, and the newscasters are like, I don't want them taking naps when they're getting paid, and I'm like, do you want to die? Yeah. It's like, no, they can take a nap as far as I'm concerned. So anyway, so now we'll put in that the number density, of course, is the number per unit volume, so that's the total number of particles times v to the -3, the volume to the -3rd power. And so this becomes then 3 to the 4/3 when I pull the 3 out of the parentheses there, pi to the 2/3 when I group the pi's together, over 4 times h bar c times the total number of electrons to the 4/3 power times the volume in which they are confined to the -1/3 power. Is that right? -1/3? I guess, oh yeah, that's right, because I was forgetting about this v right here. It's also multiplied here, yes.
Why is the v raised to the -3rd?
So I'm putting in the number density right here.
Yeah.
So it's number per unit. Oh, thank you. Yeah. I was trying to do that would be like if it was the length of the box. Yeah. So you're absolutely right. I'm just being silly
Okay.
because I'm just being silly as well. Yes. And now everything works because now it's going to be so it's v to the -1.
Okay.
Yeah. Right, so then this is v times v to the -1/4, which gives us the v to the -1/3. Now it works. Woo. You feel like I'm happy, huh?
Just doing it in my head.
Yeah,
Yeah.
number per unit volume, and then volume to the -4/3
Yeah.
times volume is volume to the -1/3. What we really want is not the total energy. We just found the total energy in order to take its derivative with respect to volume, because that gives us the pressure. So the pressure, which is minus dE dV, then is equal to 3 pi squared to the 1/3 over 4 times h bar c times, so now we'll get n to the 4/3 b to the -4/3 when we take the derivative. And then I already pre-factor things into the parentheses there. Did I do that right? I think I did. I'm just reading my notes as opposed to going on my head here. Did I do that right? So, yeah, because I bring down, because I bring down -1/3 v to the 4/3, and so we've got a 3 coming down into the denominator, so you've got 3 to the 4/3 divided by 3 is 3 to the 1/3, and so that's why you put a 3 inside those parentheses right there. So, but wait, what's that? Yeah, that's the number density to what power?
4/3.
Uh-huh. To the 4/3 power. So the pressure then is 3 pi squared to the 1/3 over 4 h bar c, little n to the 4/3. And now let's do the business of rewriting little n, the number density, in terms of the z over a rho over mh business. So in other words, the thing that's going to get the box is that the pressure in this extreme relativistic limit is, because I can never write these constants enough, 3 pi squared quantity to the 1/3 over 4 h bar c big Z over A times mass density rho over the mass of a hydrogen, all to the 4/3 power. So that's the expression for the degeneracy pressure in the extreme relativistic limit.
This is the degeneracy pressure?
This is the degeneracy pressure. Yeah, remember the whole point of this is we're talking about the Chandrasekhar limit, where we want to figure out why it is that there's a maximum mass of a white dwarf, because of the fact that degeneracy pressure eventually fails to win that, to stay in stalemate with gravity. Keep adding mass to the white dwarf, and now in reality, if it's a real white dwarf, carbon is a fuse waiting to blow because the temperature reaches 600 million Kelvin and lights the fuse, so to speak. But if you didn't have it blowing itself up first, if you keep adding mass to it, the electrons are moving faster and faster. When they become relativistic, the expression for the degeneracy pressure changes compared to what it is for when they're non-relativistic. So we just did the calculation of what's the total energy of all the electrons, and remember last time, from P is equal to, from E is TBS, DE is TBS minus PdV, we had that expression that the pressure was equal to minus the derivative of the total energy, the total internal energy with respect to volume and constant entropy. That's the calculation we were just doing. We derived what the total energy was by adding up all the energies of all the electrons. That was what that integral was. We added up all the energies of all the degenerate electrons and got this expression. And then we took its derivative with respect to volume in order to get our expression for the pressure. And this is degeneracy pressure that we're studying. So it's the degeneracy pressure because we assumed all the electrons were inside the Fermi sphere and that they stayed there as we changed the volume. We're doing it adiabatically, where all the electrons stay in the same state in terms of all that's changing is the wavelengths as we shrink the box a little bit. So this is the expression for the extreme relativistic case of the degeneracy pressure. Okay, any questions? I hate that too. Stay out.
Believe you.
First world problems. Oh, I just realized I don't like wearing my nice watch when I'm throwing chalk all over the place. So I'll be back after I take my my watch off and lay it on the counter in here.
Hello, person watching the video.
Hello, future you.
I won't be watching this lecture because I'm here.
You don't know.
How many times can we say your name whenever you're going? I don't know. No, you'll have 2 whole lectures to do it.
To do what?
To reference Kyo? Yeah, you'll have the 20th and the 22nd to make tons of references to me in the video.
This is like.
Do I really want to know? I do have the video.
Yeah, no, since I'm going to be gone on the 20th and the 22nd of March, Jared was like, how many times can we say Kyo in
Yes.
referencing me? Yeah.
Yeah, we'll definitely have to do that for sure, yes. Meanwhile, keep your ears open if you hear like anything rumbling around here. It must be like Dr. Tree's trying to steal my watch. So
He's shown interest in your watch.
he never has.
Oh,
you know,
okay.
but how many of you knows I haven't? It's not like I go around saying, shut up.
Look at mom.
That's right, yes. So, yeah, anyway.
Look at all these diamonds that I have.
Yes.
It'd be a shame if someone were to want to take them.
Yeah, I had a student yesterday, who shall remain nameless, who was really trying hard to make it exactly 18 volts on the power supply for this experiment they were doing. I'm thinking like, you'd be easy to torture, you know, it's just like, you know, be a shame if this voltage change to 17.99, wouldn't it?
Some people care about precision and outcome.
Sounds like you.
So anyway, no, actually it was John. Yeah.
Let's care about perfect level, you know.
That's a hell of a proposal story, by the way. You were apparently there, Caden, talking about saying, "Oh, my little Alec was." So anyway, if you were at home, you'll just never know. Too bad. All right, so
It's a mystery.
Oh, maybe one of you. Future deal.
So it's a polytrope again, but now the polytropic index is 4/3. The pressure is proportional to the 4/3 power of the density. As opposed to, what was it for the non-relativistic case, do you remember? 5/3, as opposed to 5/3 for the non-relativistic case. As described in example 14.1, which we're going to work through here, and 14, that's a chapter we haven't covered, and we're actually, it turns out, not going to cover it, because I want to spend more time with cosmology and GR and stuff like that. It's a chapter about stellar pulsation, but we don't need to cover that chapter for us to work through how this leads to instability here, and it is worth going through. As described in example 14.1, this leads to instability. This is what makes the degeneracy pressure no longer do the trick for us. So, this will be a little involved, but it's worth going through so that you can expose to a perturbation calculation. This is a very common technique for determining whether or not a system is stable or unstable, and on what conditions it makes the transition from being stable to unstable. It's a nice example of such a thing. And so here is our scenario. It's a simplified scenario, but it contains the essential physics. And you can use the same thing to figure out if a star is stable or unstable to pulsations. Pulsating variables are studied in a very similar way. So, to keep things simple, what we're going to do is imagine, so I guess you get a chuckle. So here is a shell, a thin shell whose mass is little m, and we put, so you can think of that as like a shell near, say, the surface of the white dwarf or a star, for example. So we're going to put all the mass of the star concentrated at the center. And in between that shell and all the mass concentrated in the center, we have massless gas. Okay, good luck with that, but it just makes this calculation simpler. We're just going to pretend we could fill it with massless gas so that all the mass is concentrated in the center, and there's this magic massless gas that's exerting the pressure holding up that little shell. And we'll say that capital R is the radius of the star slash white dwarf. Slash cube, that's right, yes. Yes, the radius of the cube is R. Yes.
This spherical cube.
I first imagined a spherical cube.
Yes.
It's not a halfway.
So let's write down Newton's second law for our shell of mass m. Mass times acceleration, m d squared r dt squared. So in other words, if it's moving inwards or outwards, it could do so with some acceleration. M d squared r dt squared. So that should be due to the combined effects of gravity and pressure. So gravity will be pulling inwards, and so it will tend to contribute, and so it will contribute negative acceleration to our shell. So that'll be minus g times the mass of the star times the mass of the shell divided by the distance squared from the center. And pressure is pushing outwards along our shell, and the total pressure force will be the area 4 pi r squared times the pressure, because pressure is force per unit area. So surface area 4 pi r squared times the pressure will be the total outward force on that shell. Now, strictly speaking, we're being a little cheaty here because so really Newton's second law applies to the motion along a particular path for a small particle, not for an entire shell. But on the other hand, it's okay because what we should strictly speaking do is consider a little chunk of the spherical shell. And we could write this expression right here, and I could call this like a little d sub m, a dm I mean, and I could put a dm right there. And I could put a little piece of area, the area of this little chunk right there, times the pressure would be the outward force on our little dm. And this would be a dm right here. But if I add that up over the entire shell, I just get this relationship. So it's okay to use this relationship. This is what you get if you consider a little dm and do it right, and then you just integrate over the surface of the shell. You integrate over the shell, this is what you'll get. When I add up all the little dm's, I get the total mass of the shell. When I add up all the little pieces of area, I get the total area of the shell. And when I add up all the little dm's here, I get the total mass again. So it's cool, in other words, is what it comes down to. So, my first question is, any questions about that? Or are you okay with what this expression is saying? Are we okay? Everybody's okay? Okay? All right? mass times acceleration equals gravity force, which is inward, plus pressure force, which is out. That's what that expression is saying. I should probably just add to my picture, like I had in my notes, by the way, that the pressure is P inside that massless gas. So now we say, okay, in the equilibrium situation, what do we want the total force on the shell to be? Zero. We want pressure and gravity to balance each other. So equilibrium would say that G big M little m over R naught squared, where the naught subscript says equilibrium radius, the radius where everything's in balance, should be equal to 4 pi R naught squared P naught, the pressure that exists when the equilibrium radius is the radius. So R naught is the equilibrium radius, E naught is the equilibrium pressure.
Does that imply that pressure's P?
So the idea is that, so what we're studying here is the stability of the system. So for example, here is a system in equilibrium. In other words, it is just hanging straight down. Everything's great. Is this a stable equilibrium or an unstable equilibrium? If I displace a little bit from the equilibrium, it goes back towards the equilibrium, right? The torque on it is back towards the equilibrium, okay? Okay, now, I'm going to have to pinch this because this is not a stable equilibrium, but in other words, in principle, I could balance this perfectly and have it in equilibrium again. If I could make it perfectly vertical, the gravitational force would be right along the axis, there would be no torque on it, and it will be in equilibrium. But is that a stable equilibrium? If I displace it away from the equilibrium, the torque wants to make it go further from the equilibrium. So, stable equilibrium versus unstable equilibrium. If you have a stable equilibrium, perturbations, small displacements, if you include damping, die down. Right? If you don't have damping, it'll just oscillate forever, but if there's any damping, it's going to die down. Unstable equilibrium, not so. Make a little displacement and it just grows. That's what we're looking for, is this in a stable equilibrium or an unstable equilibrium? Meaning, okay, if I squeeze it a little bit, then what is going to happen to the pressure? What happens when you squeeze a gas? Pressure will go up. What will happen to the force of gravity on the shell, which is now closer to the center? It goes up too. So the question is, if it's stable, and I squeeze it, if it's stable, will the pressure have gone up more than the gravity, or will the gravity have gone up more than the pressure? If it's stable, the pressure will increase more than the gravity did, so that there will be a net outwards pressure force that will tend to drive it back towards the equilibrium radius. And flip it around, if it were to expand, then we would want the gravity to have gone up more than the pressure did and have it come back again. If it's unstable, when I squeeze it, the gravity will rise more than the pressure and it will keep wanting to fall. It'll keep wanting to shrink. So that's what we're studying here is stability. What are the conditions for it to be stable versus unstable? Well, what we will do is assume the gas is a polytrope and figure out, based on that, given what happens, essentially. So, bear with me, we'll do it, but we'll determine what happens when you make a small change to the system. This is called perturbation analysis. Perturbation analysis allows you to figure out when the system is stable versus unstable, and if you find that it's unstable, then you need to switch to a more sophisticated nonlinear analysis to find out exactly what happens, because perturbation analysis assumes only small changes. If the system is stable, small changes stay small changes. But if the system is unstable, small changes become big changes, and you quickly get into a situation where the simplifications you make based on the changes being small are no longer valid once the changes become large, is what it comes down to. Okay? So, let's do it. Let's make a perturbation. Okay, perturbation. We're going to perturb the system in the physics/math sense, which means to make a small change in it, as opposed to, everyday English. To perturb somebody is to piss them off, right? But that's not what we're doing. In a sense, it's like, is that life stable or unstable? Let's perturb it. Unstable! Make a perturbation, a small change.
A small change.
Yes. Let's slightly annoy the system and see, is this system chill
Or not chill.
not chill? Yes.
Physics for millennials. Is it chill or is it no longer chill?
Yes.
Next week's lecture we'll discuss, is it lit versus is it not lit?
That's what it
We're
started.
talking about a type 1A supernova, right? Oh man, it's
That's
lit.
lit.
Yes.
Neutron star, not lit.
Right. Exactly.
I'm just saying, well, as soon as you just go through this, man, that's lit.
Yes, that's exactly what it
Famous
is.
quotes.
Yes.
Man, the star is lit.
So we should write this down, if they ever discover something, just so it was, like, the textbooks happen at the same time.
Yes, exactly. That's right, yes.
Charlie Martin is famously quoted as saying, wow, that's lit. When you discover it.
Yes.
Wow.
We're gonna do that.
It's fun to talk about now because you know that's never.
So, R goes to R naught plus a little change delta R. P goes to P naught plus a little change delta P. And this is pretty common notation, is to use that kind of delta to represent these changes. And it's very similar to what you see like for like when you do mechanics and they do the variations,
We
right?
just did this today.
Did you? Did you really? Okay. All right.
Yeah, kind of similar. Well, I mean, just the same, like, notation
Mhm.
is used today.
Yeah. There's going to be, we're just like, Reese and I are like,
Yeah. The O connection.
yes. So we put those into our equation of motion. If we make those small changes, R is now equal to R naught plus delta R. So md squared quantity R naught plus delta R dt squared is equal to minus g big M little m over R naught plus delta R quantity squared plus 4 pi 5 times R naught plus delta R squared times P naught plus delta P. This is not any kind of approximation. This is exact because R naught really is. R really is R naught plus delta R. P really is P naught plus delta P. So far, this is exact. But what we're going to do is say, okay, but if the perturbations are small, let's do the Taylor series thing and only keep the lowest order terms, is what it comes down to. So if delta P over P naught is much, much less than 1, i.e. delta P small compared to P naught, and delta R over R naught is much, much less than 1, we can make some approximations. And since that takes low, I'll come over here. So 1 over the quantity R naught plus delta R squared is equal to, let's factor out, 1 over R naught squared, well, I'll just make an extra step compared to what I have in the notes. So this is 1 over R naught, factor out R naught times 1 plus delta R over R naught, quantity squared. So I'm just factoring out the R naught in the bottom.
The only thing that's missing from here, between this thermal is taking the LN and then doing this.
Yeah, we're not going to take any LNs here, but you do like Stirling approximation.
Yeah, we had very, very large numbers, so we took the LN.
Oh, you're doing entropy, like Stirling approximation, all that
Yeah,
kind of stuff. Yeah, taking the LNs. Yeah.
I'll just throw that in there.
Yeah. No, I'm not doing that here. Yeah, doesn't matter. So notice then I can say that that first piece, that first term, the 1 over R naught plus delta R squared, that's 1 over R naught squared times the quantity 1 plus delta R over R naught to the minus 2, because it's down into the denominator. Oh, but wait, now we can do the Taylor series approximation thing, or the binomial theorem thing, take the thing. It's the same thing, it's the other, comes with the other. But anyway, so this is 1 over R naught squared. Delta R over R naught is much, much less than 1. So I can use the 1 plus x to the nth power is approximately, right? If x is very small, 1 plus x to the n is approximately,
So 1x plus x, or nx.
1 plus nx, right? That's what you get to do. So we'll do that here. Here, x is delta R over R naught, and n is minus 2. So this is 1 minus 2 delta R over R naught. And then for a term like R naught plus delta R quantity squared, P naught plus delta P. Well, if I did it exactly, R naught plus delta R the quantity squared, of course, is R naught squared plus delta R, the quantity squared, plus 2 R naught delta R, and then I'm going to multiply that by P naught plus delta P. But here's the thing. If the idea is, if delta R is small, delta R squared is, so to speak, very small. Right? In other words, what we're going to do is throw away terms which are quadratic in the differentials, the perturbations, I should say. We throw away terms that are quadratic in delta R and delta P. Quadratic or higher order. In delta R and delta P. Such as delta R squared, well, in other words, well, such as I said, or higher, delta R squared, delta P squared, delta R times delta P. We throw away terms like that. We just don't keep them. Because they will be small compared to all the other terms in the expansion. So in particular, when you do an expansion like this, you would say, okay, I'm not even going to worry about that delta R squared. So I can make this into R naught squared plus 2 R naught delta R. And then I'll multiply by P naught plus delta P. And then there too, when I expand it out, I'm not going to keep the 2 R naught delta R delta P because that's got delta R delta P in it. It's got 2 small terms in it, and so I throw it away. A product of 2 small terms is very small compared to ones that don't have products of 2 small terms in them. So this becomes approximately, when I expand out, when I FOIL this, when I do Nunn-Hungarian expansion. You guys know that story, right? Okay, so this will be R naught squared P naught plus what else? So what terms do I keep here? So in R naught squared P naught, will I keep R naught squared delta P?
Yes.
I will keep that because it's first order in delta P. And then there will be 2 R naught delta R P naught. Will I keep that?
Yes.
Yes, because it's also first order, this time in delta R. But then there's also 2 R naught delta R delta P, which I throw away. So in other words, in this expansion, I've thrown away all the quadratic and higher terms in the delta R's and delta P's, leaving just these pieces left over. That's where I'm making the perturbation approximations. That's where I'm approximating using the fact that the disturbance is small. And that's legitimate as long as the disturbance stays small. But in other words, what we're going to get is the condition for does the disturbance stay small or not. Initially, you can always get away with those approximations, but if we discover that the differential equation implies that those are going to be exponentially increasing instead of sinusoidally oscillating, then we have an unstable system. We're going to get, notice we got a d squared, dt squared term in there. Basically, the question is, does the system act like a spring? Is there a restoring force so that it oscillates? Or does it act like a system where the ball is on the top of the hill and wants to roll away? Does the system act like a ball rolling on the bottom of a hill, the bottom of a valley, or does it act like a ball on the top of a hill? If the ball wants to roll away, then it's going to get exponential growth initially versus oscillation. And that's the border we're finding condition of which regime we're in. Do small perturbations grow or decay with time? Is the question. Oscillate if you don't have any damping. But damping in, damp. Okay, any questions? Okay. We have an exciting break anticipating what's going to happen next. Ooh. So person at home, like, wait a few minutes to build your excitement. Don't just play the next video.